I'll just do it here. If you've anytime you've got 12 inches, you get back 1 foot. If you had x feet, you would get x times 12 inches. So this is an identity where you can exchange a certain number of feet for a certain number of inches. And the list goes on and on and on. You could exchange gallons, whatever, feet, mother-in-laws for whatever. I'm just kidding. I love my mother-in-law. She's awesome. You could exchange feet to yards. You could exchange gallons to liters, dozens to half dozens, whatever. The number of things that you could exchange is infinite. Every time you've got an equation, really you have an exchange rate. You say every amount like this is equal to this amount. So really every single time you've got an equation, well, you've got an exchange rate. And if the exchange rate holds for all possible values of x, we call that an identity. Again, all with a little asterisk. So what in the world does that mean to our class? Well, here's the punchline. Suppose I ask you, hey, I've got sine square x, and I want to take it into my exchange house. How many cosine square x's can I get out of that? Or how many cosines? Chew on that. What would be the exchange rate for sines x if I want to turn them into cosines? Or if I had a tangent x, could I exchange it for some cosine sides? Suppose I bring it to the exchange house and I say, hey, buddy, I got a few tangent x's in my pocket. I want to exchange it for some sines and cosines. Could you help me out? Could you help out a brother? And then they'll say, what? You're crazy. But in fact, there is an exchange rate. There are formulas that tell you exactly how tangent of x for any value of x, well, any with little few exceptions, is equal to some certain values of sines and cosines. That right there, that's the powerful way of looking at it. Incredibly powerful. Believe me, it took me hundreds of years to think about it in that way. And you'll see why. Anyways, I'll let my hands do the talking. Watch this. Once we've established exactly what an identity is, we gave these two powerful ways of defining identities. One way to define it is an equation where you might have some variables, but the equation to be an identity has to be true for all possible values of the variables. Okay, for all possible values. Again, with some exceptions that I'll get to later on. I should say with all applicable values of x. That's a powerful way of looking at identities. They're just formulas that are always true. Second powerful way of looking at identities is their exchange rates. Every time I give you so many mother-in-laws, I get back so many. Every time I give you so many sines, you give me back so many cosines. Or every time I give you so many x's, you give me so many y's. Every time I give you so many British pounds, you give me back so many US dollars, etc., etc. Okay, these are really, really powerful ways of looking at identities. And once we've got that down, the next thing to do is probably look at a few examples, and then I got some more stuff for you. So let's just take baby steps here, small steps. Give me some examples. So take this example: 3x plus 2 is equal to 5. And a lot of times, one of the crucial questions will be: is it an identity or not? Yes or no? Again, this is just practice in identifying what is and what's not an identity. To be an identity, it has to be true for all possible values of x. All applicable possible values of x. Is this one true for all x as well? Let's see. If x is equal to 1, that would be 3 times 1 plus 2 is equal to 5. Yes, it's good. Maybe we just got lucky. What if x is equal to 0? If x is equal to 0, this 3 times 0, 2 is equal to 5. Uh-oh. Uh-oh. What happened here? No. So this guy is not an identity. In fact, this leads to another important theme, is that whenever you have an equation and you want to establish that it's not an identity, an easy way to do it is to find some x values for which it doesn't work. If it doesn't work for some real x values, then, well, there's more to that, but I'll tell you more about that. If you find a few examples for which it doesn't work, or even just one example where both sides are defined and it doesn't work, you've got it. You've proven that this formula is not good for all possible values of x. In fact, this one is only good when x is equal to 1, so that's a traditional equation. They're sometimes called conditional equality. This is a conditional equality. The conditional means that it's only true when x is equal to some values, not all of them. Okay. Let's you guys want to do another example? Let's try this example. Clone. So we could try another example. Try this one. Suppose you have 2x plus 20 divided by 2 minus x, and that's equal to 10. Is that an identity? Yes or no? That's the big question. Is it an identity? Yes or no? And so one silly thing that you can try is just try some values of x. This doesn't prove anything, but it just might point you in the right direction. If x is equal to 0, does it work? If x is equal to 0, let me see, I would get 20 over 2 minus 0. Is that equal to 10? Yes or no? I reckon it is, so it does work. That doesn't prove anything. It doesn't prove it's an identity. It just proves that it was true for x equals 0. If x is equal to 1, that would give you 22 divided by 2. Let me think. 22 divided by 2, that's 11, minus 1, that's equal to 10. Yes, it does work for x equals 1. Still, that doesn't prove an identity. It just proves that it was true for x equals 0 and x equals 1. After a while, you think, well, even if I show that it's true for 100 different values, does that prove it's an identity? Not really. It just proves that it's good for those 100 values. Maybe on the 101st try, you might get something for which is not true. So this is just good numerical evidence. It doesn't really prove that it's an identity. Which leads me to the next really important part of this lesson, and that is how do you prove that something is an identity? What methods could we use? When you have a hunch, you've tried a few values, they all seem to work, and you've got a hunch, hey, maybe that is an identity. What are the possible methods that you could use to really prove it? You could try 5 values, and if they work, well, that's good numerical evidence, but it's not really a proof. It's not really that convincing in a way that we would like it to be. So we would like to study now methods of proving identities. For our class, we will have four famous techniques that I'll talk about, and these will serve you well for all your other math classes, for all your life, as a matter of fact. So here are the methods to prove when you think that something might be an identity. Here's what you could try. Okay, so the first method that you could try to prove that something is an identity, that would be, the first method is called working on each side separately. Work on each side separately until you make it extremely obvious that the sides are equal. Let me give you an example. Let's go back to, say, my aunt's example here with her. She took any number, doubled it, add 10, divided by half, subtracted, blah, 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 blah. The way she was doing it was working for every single possible value of x. We tried it for a few x's, and it seems to work. We tried it for x equals 3, and it worked. We tried it for x equals 20, and it worked. We tried it for x equals 11, and it worked. So we got this idea that, hey, maybe it works for all possible x's. This doesn't prove it. This only proves it for these 3, but here's a good way where you could prove it for all possible x's without having to check each one separately, because that would be way too many. Here's what we can do. We can say, you know what? First, this is an incredibly important step. First thing you do is you abandon the assumption that they're equal. You say, you know what? I don't know that they're equal. That's what I'm trying to figure out. And so you say, I'm going to make an imaginary line here. With flowers. No, I'm just kidding. I won't make it with flowers. I'll make an imaginary line that's blue. Blue. And say, hey, you know what? I'm abandoning the assumption that they're equal. I don't know that they're equal for all possible x. I'm going to work on this side separately, work on that side separately. I'm going to take small steps that I know are correct until I can determine, are they equal, yes or no? Okay? This is a crucial step. You abandon inequality. Watch, I'll do it again. We had equality here. Here's what you do. You erase the equality. You say, you know what? I'm not going to assume it. I'm going to work on each side separately. Okay? I'll do it again. Watch. If you missed that. If you have equality, the most important step is you abandon the assumption that they're equal. And you say, you know what? I don't know that they're equal. Let's check. That's what a mathematician does. Mathematicians love to check things. So here we go. I know. Let me think. Here, I'll take small, tiny little steps that I know are good. For example, I know that I can separate this fraction like this: 2x over 2 plus 10 over 2. I know that because I know all my algebra rules. Or said differently, if you were to add these two fractions with the same denominator, you would just add the tops and get exactly that value. So I know that part is true. I'll just say here by algebra. I know my algebra. I know also that 2 times x divided by 2, that's just x. And I know that 10 divided by 2, that's just 5. And I know that this is minus x. Again, all I did is just a little algebra. I know that this guy equals that one. I know these two are equal. And I know that these two are equal because all I did is simplify using algebra. What should I say here? I won't write anything. I'll assume that you understand that this line is equal to that one because of algebra. This line is equal to that one because of algebra. OMG. Oh no, we didn't. What is x plus a negative x over here? Can I commute these, kill these? Yes, I can because of algebra, and this just gives me 5. So, check it out. This is equal to that by algebra. This is equal to that by algebra. And this is equal to that by algebra. Now, I'm wondering, are these two sides the same? Is this equal to that? Now that I've made it obvious that I've made both sides look the same, now I can conclude they are equal and put a little check mark on it. Done. Proven. The two sides are equal. For all possible values of x's, the two sides are the same. And this, my friends, this is a proof. This is a convincing. Our proof is a convincing argument with logical steps that most people accept as reasonable, where you can convince that the statement is true, roughly speaking. Anyways, it's nice. Beautiful, huh? You want to try it again? Let's try it again. Let's try it on... Not that one. I had another one up here. Let's try it on... Let's see. Let's try it on this one. 2x plus 30 divided by 2 minus 15 is equal to x. Okay. The question is this an identity or not? Here's what I could suggest. First, try to get a feel for it. Is it true for all possible values of x? I don't know. You could try some values on the side here. Let's try some values with our magical erasing pen. If x is equal to 0, for example, if x is equal to 0, you would get 0, you would get 15 minus 15. What is that equal to? 0? Yes, it is true for 0. So then you say, hey, maybe we just got lucky there. Let's try it for x equals 1. If x equals 1, I can just do it in my head. 2 times 1 is 2, 32, 16 minus 15 is 1. If x is equal to 1, then both sides are the same. So you say, hey, maybe they are equal. And so you start to set out to prove. And our proving technique will be, let me see, which proving techniques do we have so far? Oh, we only have one proving technique. Work on each side. Why don't we try that one? So here's the crucial step. You abandon the assumption that they're equal. Whoa. Let's ungroup these again. So you abandon this, gone. Abandon this, gone. And you say, I don't know that they're equal. I want to know if they're equal. This is a crucial step. You keep this side separate from that side separate. And here you only write things that you know for sure are equal. And here you only write things that you know for sure are equal. And in doing so, you will, hopefully, you'll get to a point where you can compare the two and say, yes, they're equal, or no, they're not equal. All right, so let's see. We're going to settle this once and for all. This is for sure not a good color. 2x over 2 plus 30 over 2 minus 15. That's just algebra. I could split that fraction up. Some more algebra. I could do 2 over 2 is x plus 15 minus 15. And some more algebra. 15 minus 15 is 0, so all I get is x. Tell me. You tell me, are they equal or not? Of course. They call me the mailman because I deliver. Both sides are equal, and so that proves it. That proves it using the excellent technique, working on each side. Incidentally, well, should we try another one? One more? Working on each side. How about this one? So again, you abandon the assumption that they're equal and say, hey, I don't know that they're equal. I'm trying to check to see if they're equal. So you say to yourself, hey, I'm going to make an imaginary line here and see how it goes. I'll work on the right side now, and because I can see something famous here. The x cubed minus 1, that's a famous polynomial, has a famous factorization. X squared plus x plus 1 all over x minus 1. This is just by algebra. Now, assuming that x is not equal to 1, I can cancel these, and that simplifies into x squared plus x plus 1. Are they equal, yes or no? Can I commute these? Whoa, what? That was too many pluses. X squared plus x plus 1. Are these two sides equal? Yes, they are. I can rewrite this as 1 plus x squared. By the commutativity law of addition and some other minor things, just algebra. And this proves exactly that they're equal. The left side equals right side. And that tells you it's an identity. This is a good one because here I can point out something crucial that I've been alluding to, but I haven't really pointed out. I said an identity is a what was the interpretation? Let's go back. Let's check the transcripts. Check the transcript is what Nancy Pelosi said. All right. An identity is an equation that's true for all possible values of x. And I put a little star here. I want to talk about this little star now, the asterisk, because if you look at this one, okay, you have that. Let's just erase all this. We already proved it. We already proven that this is equal, but here it's true for all possible values of x. If you try x is equal to 2, that would be true. If you try x is equal to 3, that would be true. The one value that's troublesome here is what happens if x is equal to 1. That's a pretty interesting one, because if x is equal to 1, the left side is equal to 3, but the right side is 1 to the third minus 1, which is 0, over 1 minus 1. This is 0 over 0. And you say, what? My name is who? My name is what? The right side is not even defined. It's not even defined to be a real number when x is equal to 1. This is not defined. Not defined for x equals 1. It's not a real number. 0 over 0 is an indeterminate form. So that's exactly what I meant when I say for all possible values. This we will still call this an identity, but we will point to how we define identity. An identity is an identity if it's true, or transcripts for all possible values of x, with a little exception. Any numbers that make one side undefined, those are off the table. I'll say that one more time. No. Any value that makes either side undefined will be omitted from all the values where the equality has to be true, okay? So you could say it this way. You could call those values bad values or exceptions or special values. And we could say it this way. An identity is a formula that's true for all possible values of x, or all possible values of the variables, except for the special values. Okay? Those are the values that make either side or either portion of the sides undefined. Okay, I had to get that out of the way. But anyways, we're making progress here. How do we prove an identity? One famous way to prove it is to work on each side. Abandon the assumption of equation, abandon the assumption of equality, and just work on each side separately, taking small steps that you know are correct until you can compare the two sides, are they equal or not. Super, super, super important technique. Okay, which means I think you guys are ready for a second one. Second technique. Okay, so the second method is to what we will call tweak. To tweak a known identity. And let me explain how that goes. This relies on previous identities that you've already proven. Suppose you wanted to prove this one and you say to yourself, hey, you know what? That looks a lot like the one we proved earlier, the one that we proved, Tia Raquel's identity. You see the 2x and the 10 and the 2 and the minus x and the 5. This looks a lot like it, except instead of having x, we have 3y. So you say, hey, maybe there's some relationship. So here's a new strategy. Rather than working on each side, you say to yourself, you know what? You draw a line and say, you know what? I'll leave that for later. I don't know if it's equal or not. Okay, we don't know if it's equal. But I know I can start with something that I've already proven it's equal. I've already proven that 2 times x plus 10 all over 2 minus x is equal to 5. This one is already proven. We proved it a couple minutes ago. The absolutely crucial difference here is that you don't have to abandon the assumption that they're equal. We have already proven that they're equal. So here you can do stuff to both sides. You can do whatever you want. We already know that this equation is equal. This side is equal to that side. Not only that, but we know it's true for all possible values of x. Again, with the exception of values of x's where either side is undefined. But that's not the issue here. This is true for all values of x. All real values of x, that is. And so, since it's already proven, is it true for x equals 5? Yes. Is it true for x equals 7? Yes. If it's true of x equals a mother-in-law? Yes. If it's true, is it true for x equals 3y? Absolutely. So here's a tweak. The tweak will be substitute x equals 3y. Since it's true for all values of x, it's certainly true when x equals 3y. That would lead you to the following equation. 2, I'm going to leave some space there for the x, plus 10 all over 2 minus, I'm going to leave some space, is equal to 5. And then I'm going to make my substitution here. Instead of x, I have 3y and 3y. It says this one is true for all x's. It's true when I substitute. All I did there is substitute by substitution, and I'm done. This is exactly what I needed to prove. I needed to prove that 2 times 3y plus 10 all over 2 minus 3y is equal to 5. And that proves it. Simple idea was start off with a known identity. You make a little substitution, and this is still an identity. This is true for all values of y. Does that make sense? It's easy. This is a tweaking. The tweaking is the easiest one, probably. Here, try another one. Is this true? Well, you say, I don't know if it's true, but I know something else is true. I know if I take 2 times y plus 10 divided by 2 minus y is equal to 5. This one we already proven. We proved it for x's, but I got too many x's here, so I just chose a different variable, y's. Since it's true for all values of x's, it's true when I call that a y. And then we make a small little tweak. The tweak is to substitute y is equal to x squared plus 1. If you make that substitution, then you'll have that 2, I'm going to leave some space here for the y, plus 10 over 2 minus the y is equal to 5. And I substitute back in there. Instead of this y, I have x squared plus 1, x squared plus 1. That was the tweaking. And you're done. Just like that. Okay? the essential part of this process is you start off with something that you already know is true. Then you can move things around as you please. You can multiply both sides by any number you want and it still be true. You can substitute any values in there just about, and it'll still be true. And a lot of times that's all it takes. All you have to do is just tweak, a little tiny tweak on a known identity. Huh? Alright, you guys look like you could use a third method for proving identities. Okay, the third method that we will consider is looking at the graphs. Often, looking at the graphs provides a very compelling, convincing, and logically penetrating argument to establish identities. Let me show you. Don't worry, I got your back. Let me show you. Here's a crazy assumption. Can you believe it? Would you believe it if someone told you that cosine of any angle, cosine of, say, any angle x is exactly the same thing as cosine of the negative version of the angle? Could you believe that? No way. Yes way. Let's just do a little silly example here off on the side. What is cosine of 30 degrees? Well, you would draw your 30 degrees here. This would be 1, 2, square root of 3. So the cosine of 30 would be the square root of 3 over 2. Right? And they say, what about cosine of negative 30 degrees? What would the cosine of negative 30 degrees be? Well, you would draw your negative 30 degrees reference triangle. This is 30, this is negative 1, 2, square root of 3. Cosine of negative 30 degrees would be equal to adjacent over hypotenuse. It's also equal to the square root of 3 over 2. OMG, they're equal in this case. I say, well, maybe we got lucky. So you try some other degrees and it seems to work all the time. So you say, whoa, I can't believe it. Maybe it is. It is true. And so you set out to prove it. And here's a third technique. First one was working on each side separately. Abandon the assumption of equality. Work on each side separately till you can figure it out. Second method was tweak a known identity. That means start off with something that you know is equal. You don't have to abandon it. You just tweak it by either substituting or moving things around that are legal steps. Third method, look at the graphs. Let's see. Let's ungroup this so that we can abandon the assumption here that they're equal. Abandon it and say, whoa, I don't know that they're equal. I'm trying to see if they're equal. So you say to yourself, I know, maybe I can graph this graph. Y is equal to cosine x. And you say to yourself, well, that graph is easy. We're masters at graphing now, remember? We graph the whole bunch. We draw the little box here. Goes from 0 to 360. You remember, right? And the cosine goes like this. And we still don't know if they're equal. Let's do the other one. You look at y is equal to cosine of negative x, and you say, whoa, that's almost the same as that one, except instead of having x, I have negative x. Instead of having positive x, I have negative x. So this is a flip over the y, and you say, I know how to graph that. That's duck soup. I could do that with my left hand. So you say, okay, that's just going to be a flip. Whoa. No. Whoa. Take it easy. This would be something like this. Flipped over the y-axis, and the graph would go, let me see, what happens if you take this graph and you flip it over? It would go through, still same corner there, it would go through the opposite corner on this end. It would look like this. And the question is, are these graphs convincingly equivalent? And the answer is yes. And the reason for that is because if you were to keep going, let me see, if you were to keep going here, this would look like this. Remember, this is just one period, so it goes on forever and ever on both sides, and so does this one. And if you extend their periods, now it's easy to compare. Are they equivalent graphs, yes or no? And they're convincingly equivalent. And the answer is yes, they are convincingly equivalent. And so this is a convincing argument that these two functions are exactly the same. And so, in fact, we've proven it by the third technique called look at the graphs. If the graphs are convincing enough, sometimes they're not. And sometimes they are very convincing. And sometimes there's a matter of opinion on what really is a proof and what's not a proof. The only opinion that counts is mine. I'm just kidding. Everybody, I love, I don't mind accepting other people's opinions, but in my opinion, if you're interested, and I think these are convincing arguments, and I would consider this a proof, and so would probably most regular folks out there. So then that's a proof, and that gives you your third way of looking at it. Either you could work on each side, you could tweak a new identity, or you look at the graphs. And I want to say something more about this. This is going to become really, really famous pretty soon. So this tells you something really, really, really important. Really, 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 really important. Remember our second characterization of identities, this exchange thing? What did we just learn about these then? See, let's delete all this funky stuff here. What did we just learn about the exchange rate? We just learned that if you take a cosine negative x and if we bring it to the exchange house, they can exchange it for a cosine with a positive x. Ain't that something? Huh? How do you like me now? Every time you've got a cosine of a positive angle, you can exchange it for a cosine of a negative version of the angle. No problem. No questions asked. They're interchangeable. Pick one or the other one, whichever one you like. It's a powerful, powerful way to look at it. Okay? Anyways, boy, I think this video is getting kind of long. I'm running out of gas. But I got one more super, super important thing to share with you. So let me get it together. Put this on pause and come back strong. Finish off strong on the 12th round. The last one is perhaps the most challenging, the most rewarding, and it's my favorite. It's really what makes many people fall in love with mathematics, and that is when you start with something. Start with something amazingly creative and brilliant. And out of sheer brilliance and creativity, almost divine inspiration, you get ideas and you twist the ideas and change them and modify them and tweak them a little bit, and out of pure magic, the proofs come out of there. This is really, really nice stuff. If you can ever afford to just take some time and start thinking about some amazingly and brilliant ideas, this stuff feels really, really good when you accomplish one of these proofs, or even just looking at other people's amazing and brilliant ideas. It's really nice to see. It's almost like watching or listening to a beautiful poem, or reading a beautiful novel, movie. The brilliance of humans, the creativity is one of the